At this point, you should see that there is a relationship between a function, its antiderivative, and the total change of a function. In this section, we'll make this more concrete by introducing the fundamental theorem of calculus. To get started, let's take a look at what the fundamental theorem of calculus says. Let f be a continuous function on the closed interval from a to b, and let capital F be any antiderivative of little f. Then what the fundamental theorem of calculus says is the definite integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. So the difference between the function evaluated at a and b. Another way to write this is this shorthand notation, where I write capital F of x, and then next to it I put a vertical line with a and b on the end of it. All that means is put b into the function, put a into the function, and subtract the two. Remember that capital F of x is the antiderivative of f of x, so an alternate way of looking at the fundamental theorem of calculus is to think of it as the definite integral from a to b of capital F prime of x dx, so we're taking the definite integral of a rate, and what that does is it undoes the rate and gives us the total change in the function, capital F of b minus f of a. When you look at it this way, you can really see that we start with a rate, we do the area or do the antiderivative, and what we end up getting is the total change in that function. Here I'm trying to make this a little bit more concrete. So we have capital F prime, which is our rate of change of f of x. When we use the fundamental theorem of calculus, what we get out of that is the change in capital F. So we go from capital F prime to f. But the key thing to notice is when we do that, it's a change in capital F from x equals a to x equals b. So we get capital F of b minus capital F of a. Remember when we started out earlier with our problem where we had speed information here, we had things in meters per second or miles per hour. What we ended up getting here was the change in position, how far the car had gone. So this capital F of b minus capital F of a represents that change. So in words, this says that the area under the rate of change of capital F of x from x equals a to x equals b gives the total change in capital F of x from x equals a to x equals b. So let's go ahead and use this fundamental theorem of calculus to go and calculate out some definite integrals. This says find the definite integral from 1 to 3 of 3t squared dt using the fundamental theorem of calculus. So the fundamental theorem of calculus says that I'm going to be finding the definite integral from a to b of f of t dt, and what I'm going to get is capital F of b minus capital F of a, where capital F is the antiderivative of little f. So what I'm going to need to do here is I'm going to need to go ahead and find the antiderivative. So I'm going to match up little f with 3t squared. And because I know that 3t squared is capital F prime of t, if I go ahead and take the antiderivative of that, the antiderivative of 3t squared is just t cubed, because when I raise the power and divide on t squared, I get t cubed over 3. When I multiply it by 3, that just gives me t cubed. So now all I need to do is capital F of b minus capital F of a with t cubed, and a and b is just 1 and 3. So I'll go ahead and put b into my antiderivative. I'll put a into my antiderivative, which gives me 3 cubed minus 1 cubed, or 27 minus 1. And so the value of this definite integral is just 26. I don't need to go ahead and do area like I did before. Fundamental Theorem of Calculus lets me calculate the area using the antiderivative. So another way I could have written this out is I could have written the antiderivative here, t cubed. Putting the 3 and the 1 on the end here means put in 3, put in 1, and then subtract them. And this is just a convenient way of breaking up the whole antiderivative process with the putting the number in process. So now let's go ahead and find the area under f of x equals 2 to the x between x equals 1 and x equals 5. The first thing I need to do is I need to write that out as a definite integral. So when I go ahead and I find the area from 1 to 5 under this exponential function, what that means is we're going to need to evaluate the definite integral from 1 to 5 of 2 to the x dx. So in order to use the fundamental theorem of calculus, I'm going to need to know the antiderivative of 2 to the x. If capital F prime of x is 2 to the x, then the antiderivative is 2 to the x divided by ln of 2. This is one of those rules that we learned earlier. So I write down my antiderivative, 2 to the x divided by ln of 2, and I need to evaluate that from 5 to 1 and then subtract it. So I get 2 to the 5th over ln of 2 minus 2 to the 1 over ln of 2. And when I work those numbers out, I end up getting 30 over ln of 2, which is approximately 43.3. Notice how the fundamental theorem of calculus makes the process of finding area a lot easier than using left-hand sums or right-hand sums. In addition, this 30 over ln of 2 is the exact area. It's not an estimate. The only way it becomes an estimate here is when I round this number to get 43.3. But because I know that this is 30 divided by ln of 2, I can write this out to as many decimal places as I want.